This is section 8.2, part A, conditions for estimating P, or the proportion for a population. Several thousand small plastic beads, at least 2 different colors, are going to be in a container. Before class, the teacher will prepare a large population of different colored beads and then put them in a container you can't see. Your goal is to estimate the actual proportion of beads in the population that are a particular color, let's say red. So each student, if you were to do this activity, will discuss how many samples or how many they think should be in a sample from the container. Think this through carefully because you'll need to take only one sample from this container. Have one student take a simple random sample and then separate the beads into those that are red and those that are not red. Count the number of beads in each group. Determine a point estimate of the unknown population proportion P of red beads that are in the container. Now, you need to try to figure out a 90% confidence interval for this parameter. So, if we were to do this experiment, like Mr. Smith's class did, they got 107 red beads and 144 white beads. Their point estimate for the unknown proportion P of red beads in the population is 107 out of 251, or P hat is equal to 0.426. How can the students in the class use this information to find a confidence interval for P? As always, inference is based on sampling distribution of a statistic. We describe the sampling distribution of a sample proportion P hat in section 7.2. Here is a brief review of the important properties. So we first have to look at the shape. If the sample size is large enough that both n times P and n times 1 minus P, or your sample size times the probability of success and your sample size times the probability of failure, are at least 10, then the normal condition is met and we can assume that P hat is approximately normal. The center, or the mean, we're going to assume is P. That is, the sample proportion P hat is an unbiased estimator of the population proportion P. And to find the spread, we can find the standard deviation of our sampling distribution by doing the square root of the probability of success times the probability of failure all over the sample size, provided that the sample is 10% of the entire population or less. This is only going to work if the 10% condition is met. The figure below displays the sample distribution. In practice, of course, we don't know the value of P. If we did, we wouldn't need to construct a confidence interval. So we can't check whether n times P and n times 1 minus P are 10 or greater. In large samples, P hat will be close to P. Therefore, we replace P with P hat in checking that normal condition. So to check if you're normal, you're going to take that sample proportion, or your P hat, and multiply it by the sample size, and then the probability of failure with the sample size to check for that 10%, to check if the normal condition has been met. So Mr. Smith class wants to construct a confidence interval for the proportion P of red beads in the container. Recall that the class sample has 107 red beads and 144 white beads. Check the conditions for constructing a confidence interval for P are met. So the first thing we need to do is check all 3 conditions. The first one is that it's random. The class took a simple random sample of 251 beads from the container, so the random aspect has been met. To check that it is normal, we're going to do the sample size times the probability of success and the sample size times the probability of failure, and both of these have to be at least 10. Now, since we do not know the population proportion, we are going to have to use our P hat that we already found. So our P hat was 107 out of 251. So if we do 251 times our probability of success, we're going to get 107. And if we do 251 times our probability of failure, which is 1 minus the probability of success, then we're going to get 144. Each of these are at least 10, so we know that we can use normal approximations. Since the class sampled without replacement, they need to check that 10% condition. And we know that 10 times our sample size of 2,510 beads need to be in the population. Mr. Smith reveals that there are 3,000 beads in the container, so the 10% condition has been satisfied. Since all three conditions are met, it should be safe for the class to construct a confidence interval. Notice that n times p hat and n times 1 minus p hat should be whole numbers, and there should be a hat here. You don't really need to calculate these values since they're just the number of successes and the number of failures in the sample. So since we know that there were 107 successes and 144 failures, both of those numbers are at least 10, so we are good. So if you know the exact number of successes and the exact number of failures, you can check those for the normal condition instead of actually having to do n times p and n times 1 minus p. Now let's check your understanding. In each of the following settings, check whether the conditions for calculating a confidence interval for the population proportion p are met. An AP statistics class at a large high school conducts a survey. They ask the first 100 students to arrive at school one morning whether or not they slept at least 8 hours the night before. Only 17 students say yes. So remember, the first thing you're going to check is random, and in this case, random is not met. This is convenient sampling. Since they only asked the first 100 students to arrive at school, they're probably not going to have very unbiased reading because these are the students who are showing up early, so they woke up earlier, so they probably didn't get as much sleep. So the random condition is not met, so you don't have to check anything else. A quality control inspector takes a random sample of 25 bags of potato chips from thousands of bags filled in an hour. Of the bags selected, 3 had too much salt. So the random is definitely met. We know that it says they took a random sample of 25 bags, but we need to check for the normal condition. For it to be normal, there needs to be at least 10 successes and 10 failures. We know that 3 had too much salt. So if we're considering having too much salt being a success, that is not at least 10, so the normal condition is not met in this case. So you could not construct a confidence interval.